that you've just been like.
I'm recording you now, too.
Yeah, that's why I stopped talking.
That's fine. No one's gonna watch this video anyways, but hopefully you do. All right, so let's explore some random functions. So here's my random function graph.
What's this title?
As we know, we'll get to the title.
Oh,
Let's just think about exploring
One
a
of these
function
lessons.
here. And let's say, we're going from A to B. We've got some value at A. We've got some value at B. We've done a lot of things when we talk about going from A to B.
All we ever do is go from A.
All we ever do is go from A to B. We could find the area under the curve from A to B. We could find the average rate of change from A to B. We know we can do all these things from A to B. But one thing we actually haven't found is what is the actual length of the curve from A to B. It's certainly not a straight line. It is constantly changing its slope, right? It's not a perfect semicircle. And so what we're going to look for the length of the curve from A to B, and we kind of just call this arc length. I kind of hate that is the name for it, because when we think about arc length, we kind of think about circles, and I just think about it as the length of the curve.
Yeah. Curve.
That's what's going on. All right. So let's try to figure out this. Let's try to figure out a formula for this. At any moment, I've expanded this moment so we can see the moment, right? But say if we're looking at just one little piece. All right, maybe I'll try to describe what I'm trying to do.
Is it not a triangle?
Huh?
Was that supposed to be a right triangle? Or no?
Yeah.
Okay.
Yeah. So when you calculate distance, even back in geometry, spoiler, if you go back to geometry and look at the distance formula, that was just Pythagorean theorem on the coordinate plane. That's all it was. x2 minus x1 was the base, y2 minus y1 was the height, and you were squaring them and take the square. Anyways, the distance formula is Pythagorean theorem. So what we can do here,
Can you write the distance formula?
the distance formula is the square root of x2 minus x1
Okay.
squared plus y2 minus y1
That weird. Okay.
squared. And so we're taking 2 points that are not directly on top of each other or across from each other, the change in the x's, the change in the y, and we were finding the distance. We were finding the hypotenuse. And so what I want to do right here is I want to think about this curve as an infinite number of hypotenuses. Each one of them has some change in x and some change in y. Some change in x, some change in y. Over and over again. And I know there's a lot more than 8 or however many I would draw at this rate. But each one of them is going to be some change in x and some change in y. Yeah, is that fair?
Mhm.
Okay? And what we want at any moment, like if we were to think about this as just the distance right here, I know D's like a pretty horrible letter to use in this case. I'll do an L. How about that? An L. The length at any moment. Okay, the length at any moment. The length squared would be dx squared plus dy squared, because we're thinking about this as Pythagorean theorem.
Mhm.
So if I take the square root of dx squared plus dy squared, this is our length at any moment is the change in x squared plus the change in y squared. That gives us our little length. Well, I want to rewrite this. This is kind of clunky. This isn't very nice. Inside our square root, we're going to factor out a dx squared. Why do we want to do that? Well, it will make a lot of sense in a second. But when we do,
This makes way more
when we
sense.
pull a dx squared out of dx squared, we're left with 1. When we pull a dx squared out of this, that means we have to divide by it to pull it out. Notice if we were to distribute back in, we'd have that dx squared on the bottom. And if we're taking the square root of two things, imagine you're taking the square root of 4 times 7, right?
And then separate. Oh, okay, I see.
The square root of dx squared is dx on the outside. So we've got the square root. The dx is now on the outside. On the inside, we have 1 plus dy over dx squared. This is representing our length at any moment. At any moment we wanted to worry about it, we could find the length. But what do we want? We want the length from A to B. Those are x values. So we're going to integrate this from A to B. And here's our formula to find the length of a curve from A to B. We're integrating from A to B the square root of 1 plus the derivative of y with respect to x squared, and we're taking our integral with respect to x.
Okay, I followed that much better.
Yeah, I knew where I was trying to get to. I kind of stopped thinking about what I was actually doing.
Okay, I was like.
Does that make sense though?
Yes, that made
Okay.
sense.
That's good. I've always really appreciated how that kind of provides everything
Mm-hmm.
how you want. Cool. So let's do
I bet we leave it in the video.
everything. No, I gotta keep my image. Let's do a quadratic. Why not? Let's say we've got negative x squared, and we want to integrate, or not integrate, we want to find the length from, well, this is negative x squared plus 2. And let's say we want to find the length of our curve from, I don't know, x equals whatever, -1 to 1. I couldn't get any more creative than that. All right, so we're going from -1 to 1. We're taking the square root of 1 plus, what is this? -2x squared. Type it in your calculator.
Let me write it out. Okay, 1 plus.
That's
Oh, it's just, okay. So
That's-
you just took the. Okay, done.
that dy over dx is the derivative of your
Duh,
function, so
okay.
you just throw it in there, you square it. We could do some of these by hand, but integrating a square root is not always possible
Mm-hmm.
to do by hand. So a lot of times this is just going to be,
So we can just stop
Calculator.
writing. Okay.
if you can write out the integral, you better be able to plug it in your calculator.
I do know how to do that. Bye now.
That's okay.